そうとせないけれど、起きの瞬間に着動させようとするっていう。
I work at Google, and that's a Google owned computer. That's why it always logs out and has to type in a password, because they don't trust me to just leave it open and have people spy on it. So there's a Google owned computer. So if I'm spying on you right now, it's gathering data to use against you. I don't know. But anyway, I'm going to be talking about work I did with my collaborators. Jeffrey Goldstone, that is the same guy as Goldstone Bosons. If you ever heard of Goldstone Bosons, if you're a physicist, that's the same guy. I work for the same company. Okay, so I wasn't exactly sure how to fix this, so I think it's going to be inconsistent will be my approach. That might be too simple or too hard. There's nothing in between. Alright, so anyway, there's a quantum computer, and I think we are all challenged with the question about the result line. You know, what to do with it. We all put in a lot of zeros at once to get stuff out to solve hard problems. So the question that really interests me, though, is, you know, what do we really want to do with a quantum computer? I mean, I think, and I'm not really interested in something, you know, that quantum mechanics is true or something like that. I'm much more interested in asking, can we use quantum mechanics for computational advantage? Can it help us solve a problem that we couldn't otherwise solve? So I'm going to be really viewing this, my approach is really, I view myself as a quantum mechanic. You know, I'm an engineer, and I'm trying to use my real knowledge of quantum mechanics to advance computation. That's the position I've stood up today. Okay? So it's in the service of computation. And, so in this regard, let's just see, let's just go over with the difference between a quantum computer and a conventional computer. So in a conventional computer, you input a string of bits, 0, 1, 1, 0, 1, 1, 0, something like that. And that's supposed to encode some kind of problem, or an instance of a problem that you want the answer to. And then the quantum computer outputs a bunch of ones and zeros, which encodes the answer to the problem that you wish to know the answer to. Okay? So that's what a computer does. And of course, you know, what goes on between the input and the output, that's what computer science is about. And in a quantum computer, you will have an input, but instead of having zeros and ones, you have particles spinning up and particles spinning down. So spin ups and spin downs. So we input a string of ups and downs, like an up here is 0 or 1, input the string, and we turn the crank, and out comes the answer, which are a bunch of strings, which encodes solution. So this is quantum computing, that's classical computing. Okay? Everyone can see the difference? All right, good. Listening. The point I wanted to make here is that I'm really interested in solving computational problems which are encoded by bit strings and which the answer is encoded as a bit string. There are many other uses of quantum computers you can imagine, like simulating physical systems, or let's say finding the ground state of a molecular system, or trying to model a physical system with another physical system. And I think these are absolutely interesting questions, which is not the subject of today's talk. Today I'm thinking much more in terms of conventional computation, input a string, output a string, and the input is probably some kind of representation of the instance of the problem, and the output is the answer. So that's computers. Yeah. So let's move on, and I'm going to try to talk now. I'm interested in what we might do with the near-term quantum computer. So I'd like to talk about specific algorithm, which is for approximate optimization. So I'd like to talk about what that means, what is approximate optimization, and what might be able to achieve with a computer, with a quantum computer. So I'm going to be interested in combinatorial optimization. I assume a lot of you know what this is. I hope so. What this is about is this. I have always n bits, and I want you to think of n as a number of 100, or maybe in the near-term quantum computer of 20, or 1,000. But n itself is not too big. Well, since n represents bits, those bits contain 2 to the n values. So then it's 1,000, you could have 2,000 bit values, and those numbers are beyond the numbers you ever going to capture in physics. You know, they're all not 2,000 photons in the visible universe. So anyway, so let's think about it. And then, because of combinatorial optimization problems, you have bits and clauses. And what a clause is, it's a restriction on the subset of the bits. So it looks at some of the bits and says for certain assignments it's true, and for certain assignments it's false. That's what a clause is. And then when you associate with an instance of a problem, a cost function or an energy function, which, if you look at a string, this C stands for Z1 to Zn. Each of these C's takes two values. So this C takes 2 to the n possible values because it's represented as bits. And each clause, if you satisfy the output, you will output a 1 for this little function, and 0 if it does not. And the goal then is to find the C that maximum. We would like to find, help the goal to find the C that maximizes this function. Now this problem, having clauses acting on subsets of bits and trying to find the maximum of all inputs of the cost function, this is the mother of all computer science problems. This is the hardest problem in some sections of computer science. If you had an algorithm that could efficiently do this for every would be showing that equals NP. In general, finding this maximum, it's just very, very hard. They might think, well, to approach it is I'm going to have some uphill algorithm, or I'm going to try to, flip this and try to move up. But the trouble is typically you get caught in local minima, maxima. You get caught in local maxima, and you can't go up. And so obviously finding the absolute best string is very, very challenging. But, sometimes, the best is the enemy of the good. And if you obsess too much about finding the best thing, you might miss a good solution. So I want to look at something else, which is to look for a string Z such that C of Z over the maximum is itself big. And this is called an approximation ratio. So if you have a computer that outputs a string Z, where C of Z over C max is big, I mean, you can't bigger than 1. Even 1 is relatively big. But it's good value, then you might be very happy. So we're going to talk about quantum algorithms for trying to maximize this ratio. We should also there's a lot to say about this, which I will get to later, about how hard is this problem really. And there are sometimes when it's really very hard, and sometimes it's not so hard. And this is a big study in computer science for the last 20 years, is understanding the boundaries of how difficult is this problem. You just get a good solution, not the best solution. So we're going to try to be specific about that by examples later. So, I'm going to talk about the quantum algorithm, and the quantum algorithm is a gate model. And I was hoping most of you will know a little bit about quantum computing, what the unitary is, and have the basic idea of how this works. So the first thing I want to introduce is a unitary operator. This is acting on a Hilbert space spanned by n spins. So we have n spin-half particles. They span a 2 n-dimensional Hilbert space. So each, if I have a spin up in the z direction, I think of that as a 0. If I have a spin down in the z direction, I think of this as a 1. So there's a natural basis for this Hilbert space, which I guess is written down, which corresponds to speed spin particles spin up and spin down. And this cost function, which I wrote on the other slide, I should put another slide in explaining that in this language, that cost function I'm thinking of as an operator acting on states, which corresponds to strings. So if I have a string, which is up, down, down, up, like that, then the cost function acting on it multiplies it by the value of C on that string. That's what I mean by this cost function when I'm thinking of it as an operator. I've got a little hat on it. But notice, and now I would like to imagine I have this cost function, and I have some parameter gamma. And gamma is just an angle. It's something to do with pi. And I consider this operator, e minus gamma C, which I can write as a product. So C was, remember that C on the previous page, we saw as a sum, so I can write this as an exponential. So this operator, you can think of as a product of m operators, each of which acts only on the qubits associated with the clause C. Because remember I told you that clauses involve subsets of the bits. So if my clause involves, let's say, bits 1 and 7, then the associated operator here would only act on bits 1 and 7. So this is a product of local commuting operators. And the reason I'm emphasizing that is this is something we imagine we'll be able to build in the near-term quantum computer. Objects we'll be able to manage to build gates which act on, let's say, 2 or 3 qubits. You may ask me, is it important that the qubits be lined up or laid out geometrically? But let's put that aside for now. Let's just imagine that I can build this. The other operator I want to think of is the sum of the sigma x's. Computer scientists like to call instead of sigma x. So there's an operator b, which you can just think of as it's just the sum of all the spins in the problem of the sigma x's. And then there's another operator, which I'm going to call u of d beta, using the same notation, which is e to the minus I beta b. And this, because d is a sum of commuting terms, can also be written as a product. J equals 1 to n, e to the minus I beta sj. You can think of this as performing on single spins, rotations about the x direction. So this is each of these is a little 2x2 unitary transformation, which rotates each spin by around the x direction by an angle beta. Okay? And then I have a starting state, which is where I begin the algorithm. I'm giving you the ingredients of the algorithm. The starting state is the uniform superposition of all the possible string values. So there are 2 to the n strings here, because Z, remember, was V1 to the Zn. And this, even though I write it as the uniform superposition of everything in the Z direction, there's an easy way to achieve that, and that's to just line up your spins in the x direction. Because if your spins are lined up in the x direction, each spin is a uniform superposition of up and down. So the whole thing is a tensor product of up, down, with up, down, with up, down, with up, down, which is all possible combinations of up and down, which is also called the state S. So this is easy to construct, easy to construct, easy to construct in some kind of idealized world where people have built the gate-model quantum computers. Okay. So now, for any integer p, although I want to say p is small, I want to imagine that I have a bunch of gammas and a bunch of betas. So, So in other words, I have gamma 1, gamma 2, gamma p, beta 1, beta p. I just put an arrow 1 for shorthand. And now I want to consider the following quantum state. It depends on the 2p angles, and I act on the state S with first the unitary operator with the C with the angle gamma 1, then the unitary operator with B with the angle beta 1, then I do the 2, 3, 4. So there are 2p gates here, 2p unitaries, excuse me. Each of which can be decomposed into more fundamental units. And in fact, the required circuit, oops, what happened? The required, I'll do something wrong. Yeah, I'm sorry. The required circuit depth here is at most MP plus P, because you can just figure that out. Okay. Now, what I want to do here is I want to build this quantum state with a quantum computer, and then I want to see what the expected value of the cost function is in that state. So my goal, okay, so what I have an object which depends on P and the angles gamma and beta, which is the expected value of the thing I want to optimize over the gamma and beta. And so now let me define MP as the maximum I can get by varying gamma and beta of FP of gamma and beta. In other words, there are a set of angles of 2P angles. Don't think of P as too big. Think of P as, I'm going to talk about P equals 1 in a minute. So there are going to be 2 angles. So think of P as not too big. And so for any, so this is a function of just a bunch of angles. The reason they're angles is because these are integer valued operators, C and D. So when they're integer valued, the parameters, they wrap around. Integer value, the eigenvalues are integer. So if you exponentiate them, either the I something, then you can just have an angle up there, because if you increase it by 2 pi, just come back to where you are. So these are not, so these are just angles. And so there is a maximum I can get over these angles. And I call it MP. And note that MP is larger than or equal to MP minus 1. Why is that? Because if I look at MP minus 1, that is the maximum of this quantity where I have forced the last 2 angles to be 0. Because, you see, if I force the last 2 angles to be 0, I'm at the stage below. So MP is, so at level P minus 1, I'm doing a constrained optimization relative to level P. So that means the maximum can only be less than or equal to this. Okay, so that means that as I increase P, I can only make the thing bigger. I mean, maybe it won't increase, but I can only make it bigger. And then I can actually prove, but I'm not going to do this, that if we take the limit as P goes to infinity of MP, there are angles that achieve Cmax. But let's just leave that aside, because that means that if I can find angles which will achieve perfection. But it's not too interesting, because this P this is the limit as P goes to infinity, and I'm not really interested in ever constructing a computer which requires an infinite number of gates. I mean, maybe I could, there's a whole class about that, but I'm going to put that aside, but it's just worth noting. So this algorithm, well, I understand what the algorithm is. But let's think about what the algorithm is. So let's think about an algorithm now. What I want to do is I want to build a quantum state, where I define the angles gamma and beta to make C big. Okay? So let's think about that for a minute. So we could fix P and start with angles gamma and beta, those vectors, and then use the quantum computer to make this state. And then you measure to get a string Z, and accordingly you can compute C of C. And then you repeat with the same angles, keep doing that over and over and over, so that you get a good estimate of that function FP of gamma beta, and then repeat with new angles to get near the maximum. Okay, so let me go over this again, because this is a strategy which I would like to try to advocate for future quantum computers. I have gates that depend on angles, that depend on parameters. And those parameters, I specified them in this case, but let's just think more generally. I have gates that depend on parameters. And what I can do is I can make a quantum state that by acting on my initial state with a sequence of operators, so I build a quantum state that depends on those angles. But now I want to choose those angles to make something big. For example, I want that state to have the property that when I measure it in the computational basis and I get strings, those strings have a high value of the cost function. That's my goal. My goal is to measure in the Z basis, produce strings, and I want them to have a high value of the cost function. So the idea would be something like this. You build the state in the lab for a fixed gamma and beta, and then you measure the cost function by measuring strings. You have to do it a few times. Not too many, actually. We can estimate that, but that's details. And then what you do is you basically just change the angles in order to try to go uphill. And there are standard algorithms for, computer science. You learn about optimization. It's but that's a classical optimization problem now. The problem is you choose angles gamma and beta to make the cost function expectation big, but the quantumness is in building the state and making the measurements. Then there's an outer loop in which you try to increase which you update the angles to try to go to the maximum. Does that make sense as a strategy? Or not really? So let's see if we can, let's see, this is all plausible. So it turns out, though, that for P fix, you can actually classically pre-process and determine the best angles in advance. It turns out that, I mean, you're pressed for time to show this, but I'll get over this. I'm so sorry. I think what I'm going to do is I'm going to rush through these slides. So what I'm going to do is, instead of really dwelling on it, showing you how you do this, I'm just going to show you a very vague outline, and if you care about it, you'll have to read my paper. Okay? So what I'm telling you is that actually, if I fix P and I have a certain kind of problem, I can actually figure out the angles. I don't have to keep going through that outer loop. I can figure out the angles, and then I can just go to the quantum computer and measure the string. So the quantum computer, even though I can find the angles, I can't find the angles. So I'm telling you that I can determine the angles to set for the quantum computer. The quantum computer is going to run. I'm not guaranteed but I can't use that quantum computer to produce the string. So the angles that I'll try to rush through this and just give you a sense. Now, the problem I will look at is called mass graph. Is this following problem. I have a graph. The graph has n. That every vertex is connected to exactly 3 other vertices. You know, the dodecahedron or a 1 or a -1. You can think of it as putting a little spin on it. Spins are opposite. It's the number of edges in which the spins different. Anti-ferromagnet that helps you. And problems like this, they're called front step. If you have a triangle, you cannot satisfy it, because you cannot put down 3 ones and -1s for which each of the 3 edges is satisfied. Very well known. The reason it's called the cut is just a graph everywhere. This means I'm summing over edges of the graph. This bracket J takes the bracket. Is a 1, which means they agree. And of course, I'm going to 0. K divided by beta B divided by gamma C. X's that are not J or K. Because if I have 1 and 2, and I have 11,